तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Okay, we have spent about 10 lectures on seeing the various aspects first required for high speed circuits and then devices, and what we arrived at is that you need devices or materials which should have high mobility or high velocity, and we compared the various materials and finally came up and said gallium arsenide and indium phosphide, these are the two materials because of better mobility than silicon and better band gap than silicon, both these put together. Then we saw what are the dopants in these 3,5 compound semiconductors from second group, sixth group forming acceptors and donors, and fourth group behaving amphoteric way, but mostly going into the gallium site and indium site. And then we took a look at another aspect, that is the semi insulating material, which is important for high speed circuits. Then you can integrate the devices on a semi insulating substrate so that the routing capacitance can be reduced. And then we saw how to realize layers on the top of the semi insulating substrate, that one. So, that is the epitaxial layer, which ultimately we said will be the one which will be used for making the devices. Now, when you want to make these devices in integrated circuit, what you need is not merely the ability to make device, you must be able to isolate the devices from one another in integrated circuits. For example, in the case of silicon integrated circuit, very popular technique is p-n junction isolation, but when you want high performance, there also you go for semi insulating substrates. So, now let us see what are the methods which are used for isolation in gallium arsenide based mainly. Okay. Very popular technique is of course the epilayer growth on semi insulating substrate and then H islands. I will just go into that in the form of figure. It is very easy to understand. Semi insulating gallium arsenide wafer cross section, on the top of that grow epitaxial layer, mostly n type layers are grown because n type materials are used for devices which operate on the transport of electrons. Then using a photolithography technique and etching, you remove the materials from these portions, so that each one of them is isolated by the other one. Each one is an island, separated by this gap, and this portion which is connecting them is semi insulating. It is not insulator, but semi insulating. Therefore, the isolation between these two layers is very good. Now, you can make the device. In each island you can make one device, put them together so that they are isolated from each other. This is the first method, which is very popular. Sometimes people may object to a structure like this, because the wafer top surface is not planar, it is varying like that. That is objectionable if this layer becomes too thick. If it is say 0.1 micron of that order, you do not have to worry much, because that step anyway you get in the oxide itself in silicon technology. But even there, when you want to go for more and more packing, reduced dimensions, then you do not like these ups and downs at all. You have to do some planarization technique. Here there is a totally different approach is there. Selective, that is the second approach, is selective implantation of dopants into semi-insulating gallium arsenide to create active regions isolated from each other. Let us take a look at the diagram. That is the second approach, what we just now read. Semi-insulating substrate, mask all other portions except these regions. The arrows show the regions where this arrow, these two regions are the regions where you implant n-type impurities, maybe silicon. And when you do implantation, you have total control on the number of atoms that you are putting there. You can virtually count. You count by measuring the current. When you implant, there is a beam current. Okay. So, if you implant for 10 seconds, I into T gives you the total charge divided by Q gives you the number of atoms that you have implanted. The atoms come in the form of ions, but when it comes and implants on the wafer, the path for the beam is in that direction, ionized path, but it is neutralized. It does not remain as positively charged, it is neutralized by electrons coming from the back door. So, current flow is like that, path complete. So, you have the electrons coming in neutralizing that. So, what you have finally, even though you are implanting ions, what you have finally is the atoms themselves, neutral. Because there is one question which sometimes people have in mind, that is I just mentioned, there is electrons coming from the back side. So, you have this N region which is implanted, and each one of them is isolated by this, perfectly planar. Okay. You can put oxides in between or dielectric layers in between, okay, but that may not be necessary at all in this case, because this is semi-insulating material. This is a very popular technique. In fact, you do not need any other equipment virtually, because you have an implanter, you can implant whatever you want. One single machine can do implantation of beryllium, in the case of silicon, phosphorus, etc. Here you can implant silicon or sulfur, whatever you want you can implant with a single machine by controlling the path of the trajectory of the implanting ions, because the mass is different, that governs the voltage and the path. So, you can choose particular implanting species. At a time, of course, you implant only one. So, there is no question of choosing between them, but once you choose the material, you have to make certain adjustments so that the particular curvature is path of is followed. I am not going into details of implantation. So, that is more involved into maybe a couple of hours you will need for that. Let me skip that, but general idea is you implant these ions, you get planar structure. Okay. Now, the story is not over there. You implant the dopants and selectively here and leave it, you do not get anything, because this implantation is done at, particularly implanting to gallium arsenide, you need high energy. Okay. Implanting onto silicon, if it requires certain energy, it requires more energy to implant at a certain depth, because silicon is lighter compared to gallium and arsenic atoms. So, when you have the host atom coming in, it will lose its energy with each collision, it will not move forward. Okay. If you remember the particle dynamics, okay, M1, M2 product is the one, the energy proportional to product of the masses, the energy transfer with each collision. It is like elastic collisions or inelastic collisions, the atoms coming and colliding depending upon angle. Maximum energy is lot when head on collision is there. Okay. So, that is proportional M1 and M2. So, that is why heavier masses you lose energy, and if you want deeper implantation, you are more involved. So, higher energy implantation systems are used for gallium arsenide implantation. Now, because of that, as I said now, when the implantation takes place, the guest is not kind to the host, okay, because it has a lot of energy. It knocks out lattice atoms from, knocks out atoms, host atoms from the lattice. So, once that is done, it is damaged thoroughly, one. Number two, these atoms which you are implanting do not go and sit in the place where it is supposed to go and sit. it is supposed to go and sit in the lattice. It will go and sit wherever the space is there, in the interstitials. So, what you must do to recover the damage and also to recover the dopants which are implanted into lattice sites, you have to give some energy. After all, the tendency of the crystal is that crystal structure that we have discussed. Why is that crystal structure there? That is the minimum energy, that the minimum energy which it takes to occupy that position. Any body will take minimum energy position if you allow. Okay. So too are the crystal atoms. Now, these bombarding atoms have knocked them out from the lattice. Now, to go push back to the lattice site, what should you do? You give some energy for that to go back to the natural site, that is thermal heating. So, you have to heat in this case anneal, that is annealing at temperatures like 900 degrees centigrade to recover the damage and also to recover the dopants into the lattice site. And you can't think of annealing. Silicon annealing you won't care. 900, okay, that's perfectly all right, there is no problem, because vapor pressure of silicon is very low, you don't lose. In the case of gallium arsenide, you have got two species, gallium and arsenic. I keep on repeating this, reminding you that this is a compound semiconductor with the two elements which have different vapor pressures. So, you tend to lose more of arsenic. So, you must put a cap. That is what is meant by cap. And so, you must put the cap, you must put the cap on the gallium arsenide surface. Okay. So, that is, put a cap of dielectric material, preferably the nitrides or phosphosilicate glass is supposed to be very good cap. Okay. So, you put the cap on the surface to prevent the loss of arsenic, or you can use some arsenic overpressure during annealing. These are the tricks which is done, which are done to prevent the loss of arsenic. So, this one must remember, the game is not over just by implantation, it is the beginning of the whole thing, because you have to anneal and suffer from the loss of arsenic unless you take care of it. Then the third method, which is done, is again epitaxy. See, epitaxial layer, when you grow, the benefit is you get a nice layer. When you do the implanted layer, the doping profile is not uniform, it has a Gaussian profile, and there are damages which are created, you have to recover. However much you recover, there are some damages left out. You can't go to 1000 degrees centigrade and all that for annealing. So, what people do is, there is another approach which is used, is epilayer growth on gallium arsenide, semi-insulating, instead of selective dopant implantation, which forms the active region. Okay. You implant, or you create the isolation region by damaging the implanted layer. I think diagram will make it very clear. That diagram. Semi-insulating gallium arsenide, epilayer. Step is same as the first one. There you are etching. Now, instead of etching, what you do is you implant proton. 100 kiloelectron volts will give out a micron proton implantation. Proton is nothing but H plus. H plus ions you implant. Implantation energy is from 100 kiloelectron volts right up to 3 million electron volts, depending upon how much depth you want the damage to take place. So, those atoms actually what they do is they are damaging the region. If this region is damaged, whatever dopant was there in the epilayer is knocked out and total chaos. It is virtually amorphous, not even polycrystalline, and that has got very high resistivity. In fact, you can turn these regions, these in between regions, you can turn them into regions where the carrier concentration is something like 10 to the power of 11 per centimeter cube. That's virtually semi-insulating. So, you can get 10 to the power of 11 electrons per centimeter cube, that level you can go by bombarding with proton. Do not think of annealing it now. If you anneal it, you have to go to much higher temperature, then that will recover and the epilayer will come back. Okay. So, do not anneal it, bombard it, low temperature annealing will not do much. Okay, so these are the three different approaches used. Okay. Very popular technique still is this one. One type of implantation species are used. We have in India, for information for all of you, there is one company called GaAs, gallium arsenide technology, okay, in Hyderabad. There they make MMICs, monolithic microwave integrated circuits for gigabit logic circuits, okay, gigahertz frequency range. That is done mainly by implantation. Okay. I am not sure whether they use proton implantation also, but they do not have epi, so naturally they do not use proton implantation unless they import epi layers and do the thing. But this is simpler. They do this particular aspect. Definitely I know that the one of the approaches that they use. They have made devices mainly for commercial defense applications. Okay. So that means now we know how to make these layers isolated from each other on the semi-insulating substrate on which you can make the devices. What are the devices that you will make on that? If you think of your silicon guy, you will immediately tell, okay, MOSFET, field effect transistor. If at least one is a field effect transistor, because today the MOS logic is dominating, but it is CMOS logic. So, okay. So, field effect transistor you will say. Other devices which are used in circuits like emitter coupled logic or some linear circuits are the bipolar transistors. And when you have the ability to grow heterojunctions with 3-5 compound semiconductors with the ternaries, you can have heterojunction bipolar transistor HBT, very popular in 3-5 semiconductors, not merely 3-5, 4-4. Silicon germanium with silicon, you make HBT. All that you need to do is make the emitter region with a wider band gap compared to the base region. So, there they will have silicon germanium base, silicon emitter, because after all you know that germanium band gap is smaller than that of silicon. So, silicon germanium will be somewhere in between. Okay, so that is the base. So, HBT, we will have ample occasion to discuss these things during this course of our discussion. Now, let us see field effect transistor. If I am going to say, you can see the options open up. MOSFET, metal oxide semiconductor field effect transistor, okay, that is a very popularly known MOS field effect transistor. You would like to do that because that has been a success story for silicon. Do you like to do that in gallium arsenide is the question. Then metal semiconductor field effect transistor, MESFET, metal ME, S for semiconductor field effect transistor, and junction field effect transistor, JFET. The moment you say FET, there are three options: MOSFET, MESFET, JFET. Which one will you choose? The choice depends upon your ability to make those devices. Okay. Other one, of course, which is completely proprietary of the 3-5 semiconductors is HEMT, high electron mobility transistor. People call this by several names. Okay. 2-dimensional electron gas FET, TEG-FET, that is another name. Enough jargons thrown out at you to, okay, but very popular name is HEMT, because it tells you what you get out of that. You get electrons which have got high electron mobility. Now, let us go to ask ourselves among these FETs, can MOSFETs be realized with gallium arsenide and indium phosphide? The answer is straightforward. They have not been successful due to the problems related to native oxide of gallium arsenide and indium phosphide. What is native oxide? Native. You convert that substrate into its oxide, it is native oxide. Silicon SiO2 is native oxide. Whatever way you do, it need not be thermal oxide. You just convert that silicon into silicon dioxide, that is native oxide. If you convert silicon into silicon nitride by thermal process, that is native nitride. If you deposit nitride, that is not native, that is just deposited nitride. silicon dioxide also can be deposited by plasma enhanced chemical vapor deposition, okay, by cracking silane and forcing it to react with oxygen, SiO2 you get, and that is deposited. That is not native. Native is true conversion. Now, the success story with silicon is you have been able to get the oxide using native oxide. Just to make it more, okay, there why I want to bring it out is you will have a p-type material, and then you can see everywhere you have got these I will show one device which you are all familiar. Right there you have got the native oxide, that colored one, field oxide, silicon dioxide. This is silicon. And then you have got the thin oxide, which I am putting it here after all the lithography and everything. That is the gate oxide. Best, okay. Then you have this gate, and then you have the, for completeness sake I am drawing this. Point that I am trying to make out is you have the source, you have the drain, and you have the gate. That is the MOSFET. What are we looking here? We are getting excellent performance because of this oxide. The entire success is because the interface between this oxide and silicon is very clean. Okay. The charges in the oxide are minimum, that is, it is close to the ideal insulator, not exactly ideal. What is an ideal insulator? Zero charge within that, and a very clean interface. There is no charges which will be staying at the interface, that sort of thing. So, when we say due to the problems related to native oxide of gallium arsenide and phosphide, the problem related to this property of this oxide and the interface. First time when they made MOSFET, I think you should know the story behind how the transistor was invented. Shockley Bratton invented transistor. It was not deliberate, in the sense it was sort of accident. They were trying, the first device that was proposed was MOS, mass field effect transistor. What was conceived was you put an oxide, a dielectric material, they were trying germanium, put a dielectric material on that, put a metal gate on the top, then you must be able to control the region below that. By applying voltage between these two, you can control the region between these two. For example, if you apply plus, you can deplete. You can apply minus, you can accumulate plus charges. That was the idea. But when they made the devices like that, it never worked. It never worked, not even a sign of current flow. Okay? Immediately, Bardeen came up with the theory that the entire problem is due to the interface between the dielectric that you put, it's just a dielectric which is deposited, and the substrate. That was the theory that was put forward to, that is characterized by a parameter called interface states. Okay. Like you put, when you put, these are all relevant for our discussion, like when you put a conduction band and valence band. Okay. If I have a level here like this, that is one level only throughout the bulk material. But if I have levels like this, continuous levels, this is surface. Those are here, and you can see one level there can create havoc in the performance of the particular device, either beneficial or not beneficial. One layer you put, donor level, it donates electrons. See, if there are many levels are there, what will happen? For example, if you take a free surface of semiconductor, how many atoms will be there per centimeter square? Almost about 10 to the power of 15 per centimeter square. then how many states will be there? As many states will be there, maybe into 2, spin up, spin down if you take. So, those are the states which are present, and those states are represented here. I will come back to this again later when we discuss about the Schottky barrier diode. So, this is the idea. That was the problem. So, if you put a deposited material your problem, you grow a thermal oxide, that was sorted out immediately. In fact, the transistor was invented because when they said there are surface states here, these are the surface states. If it is in the free surface, you call it surface state. If it is between oxide and silicon or between dielectric and semiconductor, you call it as interface state. It is the same. Okay. So, these interface states were the problems when they tried to make these transistors. Now, they tried to analyze that. That's how when they were analyzing that, what they did was, maybe it's with 1 or 2 sentences I will mention to you. N-type germanium was there. They put a probe onto one end. Between the substrate and the probe, they applied the voltage. I don't know whether you heard the story before. If you are not, just a minute I will spend on the thing. N-type silicon, germanium they put. Then what they did was, they put a contact here, back side. Then they put a probe. Heat it locally, it becomes a sort of PN junction, like a point contact diode. Old days, all the detectors were point contact diodes, that type of thing. So, this actually virtually like a P-type material. And then they applied a voltage between the two, okay, a small voltage. Maybe they put a resistor in series, so it limits the current. Now, this is a surface. What they theorized was that there is a potential distribution on the surface due to the potential established here. So, they were trying to probe ammeter. See, this is a very interesting story, that is why I am just telling you how things have come up in the transistor. This probe, they were moving and seeing whether there is any current. They wanted to see whether there is a current. So, they found when they moved here closer and closer, their current increased, and then they found when they vary this voltage, that current changed. This is a PNP transistor, okay, emitter base collector. So, that came because of the desperate study on this MOS device. Okay, this is very short. Okay, I am sure they have spent months together in doing that experiment and trying it out, but that is what happened. That is the whole benefited industry is electronics industry because of that one research. Nobel Prize, Shockley, Bardeen, Brattain. Okay. I think Brattain is still around. Shockley and Bardeen are no more. Okay. So, this is the idea. Now, let us see. So, deposit in a free surface problem is there. When you have deposited oxide, there will be still problems. If it's thermal oxide, problem is not there, because those interface states, after all, what are those states, surface states due to? The atom within the bulk is surrounded by 4 neighbors. When it comes to surface, on top surface, it is 1, 2, 3 neighbors. Up there is no neighbor, so there is a dangling bond. The dangling bond is the one which gives rise to the levels. To put it in a very simple way, any loss of periodicity gives rise to a level. If you add impurities, that is loss of periodicity, it gives rise to a level. You go to surface, loss of periodicity, that gives rise to those levels, multiple levels, because it is a 2-dimensional affair on the surface. So, you get those levels because of that. Okay. Now, you oxidize that surface with the good native oxide. You do that, those dangling bonds are saturated with this oxygen, silicon oxygen bond. Okay. Immediately, you do not have the dangling bonds, then what happened is you remove those levels which I showed you, minimize them. There may be 10 to the power of 15 per centimeter square states on surface. If you take bare semiconductor, you reduce it by oxidation. In the case of silicon, you are able to get down to 10 to the power of 10 of that order. Okay. If not 10 to the power of 10, even in a poor person's laboratory you can get 10 to the power 11 today. Okay. 5 in 10 to the power 10 you can get. 10 to the 10 of course quite a bit more involved. So you can get down to that level surface states in silicon. Gallium arsenide, those problems are there. What is the reason for that? We will see first. Quickly run down to that. So, problems related to it. What are the problems related to native oxide? Thermal oxide of gallium arsenide. After all, if you succeeded with silicon with thermal oxidation, why not gallium arsenide, thermal oxide? Put it into furnace, remove it and see what happens. Okay. Problem multiple. You now have not only gallium and arsenic, which have different vapor pressure, you have also arsenic trioxide and gallium trioxide and arsenic trioxide. Those also have different vapor pressure. So, you have multiple problems. Okay. So, high vapor pressure of arsenic trioxide approximately arsenic, when you oxidize that, arsenic trioxide has got a vapor pressure of 1 atmosphere at about 450 degrees centigrade. That is tremendous. That means if you oxidize gallium arsenide, you will oxidize. Okay. Oxide growth rate is very slow below 400 degrees centigrade. So, you have to oxidize at temperatures between at least 400 to 530 degrees centigrade. I am giving 530 because this is a number that people have been using. Okay. So, what we are trying to see is where does this hurt? It would hurt if the temperature is high. If you are able to do the oxidation at lower temperatures, you would have bought it, but the oxidation rate is very slow at temperature below 400 degrees centigrade. So, people tried 450, 500 degrees centigrade, it did oxidize. They got reasonably amorphous oxide, but the result is as you grow oxide, arsenic trioxide, gallium trioxide grows, both of them grow, you lose arsenic trioxide. So, you end up with gallium trioxide alone. That is non-stoichiometric oxide. That particular oxide is brittle and also it is leaky, its band gap is low, not as high as silicon dioxide. Silicon dioxide, what is the band gap? 8.8 electron volts, it is much lower than something like 4 or 5 electron volts. So, that is why it is the film brittle and leaky. If it is very brittle, there may be pores around that because of cracking, and when there are cracks all around, if you put a metal, if there is a crack here in the oxide, if you put a metal, it is short circuit. So, that is why this is one of the problems that you have got in hand. Now, people try to overcome that problem. Okay. Let me just go back to this one more. Okay. So, you have one problem is the loss of arsenic trioxide. Now, you will say I will control that by doing the oxidation in arsenic vapor pressure or arsenic trioxide vapor pressure. Put it in a sealed tube, put a tube, one end of the tube you put arsenic trioxide and oxidize it. Okay. You do the oxidation, but when you examine that, okay, you have what they have seen is both crystalline and amorphous arsenic have been observed at the oxide gallium arsenide interface. Okay. Two things happen. One is it is oxidizing, you prevent loss of arsenic trioxide, but your bulk oxide is good. You have got stoichiometric gallium trioxide, arsenic trioxide. You probe using electron probe, you see that. You go right up to interface. At the interface, you see amorphous arsenic and also crystalline arsenic. Crystalline means polycrystalline. That means what you have is a layer here. If I have gallium arsenide here, and if I oxidize that, if I oxidize it like this with arsenic overpressure, which I thought is the solution for the whole thing, you will get at the interface, what is that? Arsenic. That is arsenic. You get arsenic. The reason stated there, the reason is when you oxidize, gallium tends to oxidize better compared to arsenic. Once to get into more of chemistry of that, what they call as simply what you can say, the between gallium and arsenic, the oxidation potential of gallium is higher than that of arsenic. Therefore, its ability to oxidize is better compared to ability to oxidize arsenic. So, if you have gallium arsenide, and if gallium oxidizes, arsenic does not oxidize, what are you left with? Arsenic. That is the arsenic that you see here, and that is the arsenic that you get at the interface. That is real bad news. Okay. If you have arsenic at interface, not because it is poisonous for you, it is because it is like putting a metallic layer between that. Okay. Elemental arsenic is suspended, it is like putting a metal layer there. It leads to what will be the result electronically? Levels. Not only loss of periodicity, you have just arsenic sitting there, you will have extra interface state densities. So, high interface state density is observed because of this excess arsenic at the interface. Okay. So, these are the problems which people faced. Now, as a result of that, you can see whatever I have said, I have put it here, so that you have it right in black and white or white and red. Presence of arsenic at the interface is the cause of, or is due to, or it is the cause of high interface state densities. It is due to the arsenic, you get high interface state densities in gallium arsenide MOS devices with native oxide. Now, you will say now, okay, thermal oxide is bad because of high temperature, etc. Why not I go and do, this was the theme people were following in 1980s. Okay. 80, 84, 85, you see, they go to the papers, they said, we will go to room temperature, do the oxidation at room temperature. How do you do oxidation at room temperature? Anodic oxidation. Dip the gallium arsenide in an electrolyte, in fact it is water, OH. Use the OH ions for oxidation of gallium arsenide. Put 2 electrodes, dip it into that. Why? All that you need is take a beaker, put an electrolyte like which contains, in fact H2O virtually, or you can ethyl alcohol or things like that which contain OH. Okay. And then dip your electrode, okay, and you make this gallium arsenide. This is platinum. Make that positive, make that anode. This is called anodic oxidation. You make the sample which you want to oxidize as anode, that is anodic oxidation. Never forget. Reverse the polarity, there will be etching. Okay. So, this is the one. When you do that, this OH ions actually get into this surface, react with gallium and arsenic to get gallium trioxide, arsenic trioxide. We will saw stoichiometric oxides. No loss of arsenic trioxide because room temperature. Okay, no loss of arsenic trioxide, but the interface, you can guess, interface will contain arsenic. arsenic, because gallium oxidase is better than arsenic. So, you have accumulated arsenic. So, now people said, okay, arsenic is there, so I do not have any problem, I can drive it out by slightly raising the temperature, okay, because it is more volatile. Now, what happened was, in the process of annealing, what was there on surface started to become crystallite. People observed afterward there are crystallites of arsenic, which is actually still bad news. So, they never got good CV characteristics. The CV characteristics in thermal or these oxides was show frequency dispersion and hysteresis. What is the meaning of these two? Okay, let us just see that before we go into many other things. In fact, talking of the thermal oxide, we in the E department also have done some experiments way back in 1986-88 in that range using high pressure oxidation. This was the PhD thesis of one of my students who is a faculty member in the E department, Nandita Dasgupta. Okay. So, she did on high pressure oxidation of gallium arsenide, got some good results, but nowhere comparable to that of silicon. All that you could get is some publications out of it. Okay, you could not do better than that, but at that time frame, that was one of the best oxides that was available. People have sorted out the problem in different ways. When they go to HBT, we will discuss that. Okay, they sorted out problems where we have subsequently a PhD came out in our department with Rameshan using that approach. That is into 1998. Okay, that also we will discuss later. Okay. Now, what we are trying to tell is the capacitance versus voltage. That is one of the most important diagnostic tools for evaluating the oxide. Make a metal oxide semiconductor, do not have to make a transistor. Okay. So, take the N type region and have an oxide here and then put a metal. So, metal, oxide, semiconductor. Okay. So, that is the MOS structure, MOS capacitor. So, that is what is happening here. So, MOS capacitor is this one. So, that one, this is N type substrate. So, if I make plus, apply plus voltage, negative charges will be accumulated on surface, capacitance will be that of the oxide. So, when I apply plus voltage, ideally that should come like that, flat, because capacitance of the oxide. I just drawing that to explain that. Now, when I apply negative voltage, if I apply negative, it looks for plus charges. So, you get depletion layer, depleted layer you get there. So, the capacitance is capacitance of the oxide, in series is the capacitance of the depletion layer. So, depending upon the voltage, negative voltage that you apply, you get this till some maximum depletion layer reaches. Let me not get down into that. Okay. Right now, what I say is it will reach maximum value, then the capacitance reaches a minimum at high frequency. Now, when we say, when you make a gallium arsenide MOSFET like this, measure the capacitance, there will be two things happening. One, okay, is the capacitance, this is of course the ideal one, at 0 it starts dropping, this may shift, that does not matter, you can always move it up and down. This capacitance, instead of giving 1, they give higher frequency, 1 megahertz, 10 kilohertz. There is frequency dispersion. Measure the CV at different frequency, capacitance is different, which is not supposed to be ideally. Ideally, capacitance only should be 1. High frequency itself should show this. That should be the capacitance of the oxide. Okay. Let me just skip that. The reason for this frequency dispersion is the high interface state density. We will come back to that later if necessary. Okay. So, right now because we are not going to do mass, we are just throwing out mass out of our range. This is the thing that is due to that. Other thing, that is what is meant by the frequency dispersion. What is hysteresis? This is frequency dispersion. Multiple curves for different frequencies. Hysteresis. That is, I will show at one frequency I will show this capacitance versus voltage, 0 capacitance. You expect it to be like this. You expect it to be like this. You will take the low frequency one. You expect it to be like that, flat. Okay. Now, what happens is, you go in one direction. So, for example, if I go up like this, at this point, you get certain capacitance. Now, let me just try to figure out. Supposing there were a mobile charge in the oxide, when I apply plus voltage, that mobile charge like sodium ion will move to the interface. So, plus charge in the interface, actually what will happen is, it will shift the threshold voltage to negative. Okay. So, if I am sweeping from this side to this side, if there were a mobile charge, when it is here, when it is negative, where does the mobile charge go? There is an interface like this. Mobile, if I apply minus here, mobile charge will move up, field is in that direction. When it goes up to the top, its effect on the threshold voltage or the CV is minimum, because there is a plus charge, negative charge induced to the metal itself. See, the difficulty comes if the charge induces negative charges in the semiconductor. The effect is maximum if the charge is near the semiconductor, because it introduces equal amount of charge. So, if I move here mobile charge negative when you apply voltage, it will move to the metal, no effect. So, if I come from this side, it will go like this. Now, if I when I reach here, applied the voltage, I kept it there, mobile charges have moved down. Now, the entire curve gets shifted to the left. So, what you would get if it is a mobile charge is like this, you will go like this, come back. Now, what you get in this case is not that. In this case, what you get is a thing like this. Okay. That is, you get like this, you get like this and like this. One of the two. Okay. Let me just put it like this. In the case of mobile charge, you come back, it comes like that. In this case, it is like that. The hysteresis is in this direction. In the case of mobile charge, how was that? From here it will follow this path. When you go to this side, it has plus charge is there. So, the whole thing gets shifted to the left when you come back this side. But in this case, it is not due to mobile charge. It is due to charging of the interface states. It is just exactly opposite. I just purposely went through that mobile charge to tell you how to figure out. It is not the mobile charge. If it were going like this, sweeping like this, then you would have said it is due to, oh, you have gone a very bad oxide, there is mobile charge. But now, since it is this is actually clockwise, hysteresis, that is not due to mobile charge, it is due to the charging of the interface states. Okay. Let me stop at that particular effect. All that I want to point out is the interface state has given rise to slow states here, and also the states which give rise to this frequency dispersion. When you make a transistor, you end up with poor transconductance, low transconductance, because after all it is a substrate which must respond to the applied gate voltage. But now instead of substrate responding, what is responding is the interface charge. Interface charge is not going to give rise to current. See, when you make a MOSFET, the channel should respond. When you have to change the gate voltage, if the channel charge responds, drain current changes. But now what is happening is, channel charge is not responding because it is shielded by this interface. So, response is by the interface. So, when the interface responds, the drain current is not changing. So, delta ID by delta Vg is small. That means transconductance is small. That is what you are looking for. You are looking for a very high transconductance. In all these devices, better driving capability means for a given change in gate voltage, drain current change must be maximum. Then it is not happening, in spite of your predicted high mobility, etc. That is the problem. Okay. So, MOSFETs actually need very excellent gate dielectric material. We do not have it in the case of gallium arsenide. Native oxide of compound semiconductors exhibit very poor interface properties. This summing up what I have said. Okay. Very poor interface states are given by that. Okay. So, reliable MOSFETs are not made with gallium arsenide in indium phosphide and also indium phosphide. I just did not say indium phosphide. Indium phosphide, the situation is worse. Why? The vapor pressure of phosphorus is even higher than that of arsenic. So, you are in more trouble with indium phosphide. So, if that is the thing, alternate choice for gallium arsenide FET, GaAs. Okay. That is the popularly known as a GaAs, not MOSFET, GaAs. What is GaAs? The GaAs is metal semiconductor field effect transistor. It can be JFET also. What is that? That is my final slide today. We will get down into more details on this next discussion. You can see here, this tells what actually it is, the gallium arsenide FET or GaAs. In this example that I have shown the semi-insulating gallium arsenide. I have shown this layer, full layer, which could be implanted layer or epi layer etched otherwise. So, you have got here source which is N plus, drain which is N plus, and then metal contact here. Okay. You have another metal contact here, and this N channel region, in between region, you have another metal coming up. So, you have 3 metals on the surface of this, 2 of them behaving differently, this and this behaving differently compared to that. What is the difference? These metal and this metal with the N plus contact are making ohmic contact. Okay. You have the IV characteristics vertically. Ideal ohmic contact is with 0 voltage you must get current, you can never get it. So, with minimum voltage you must get current, that is the ideal ohmic contact. So, that is these two, and this is also metal semiconductor contact, it is rectifying contact. So, you have got on the same device metal semiconductor contacts, 2 of them ohmic, 1 of them is rectifying. Now, what we want to see is how you can achieve this particular as rectifying. What you need is actually a rectifying contact. It is not necessary that you put a metal there. You can put a PN junction there. That is a JFET. Instead of metal, I put a junction P plus region there. That becomes JFET. I am sure you have studied it way back in several courses, even in circuits. But so, in a gallium arsenide FET, it can be JFET if you make a PN junction here. It can be a MESFET if you put a metal here. Which one would you choose? The answer is whichever is easy for you to do, you will choose in technology. In gallium arsenide technology, you prefer lower temperatures processing. You do not want higher temperature processing. If I have to put P plus there, either I have to put dopants by implantation, or I have to do by diffusion, or more sophisticated technology like MBE and all that you have to use. So, those are more complicated technology. Diffusion you would like to avoid, because that will lead to loss of arsenic, etc. So, what I am trying to point out is, because of those problems, it is the metal semiconductor technology. So, what we said today to sum up is, we have seen that even though in semiconductor silicon technology MOS has been most successful, in gallium arsenide technology MOS has been most unsuccessful. So, instead of MOS, it is a JFET or MESFET that is being used in the case of gallium arsenide devices, but in the case of indium phosphide devices you will see that it is not MESFET also. MESFET does not work out in gallium arsenide indium phosphide devices. That has got to be JFET, or the last one is the straw is the MISFET, MIS field effect transistor. In fact, there is some drive to get MIS field effect transistors in gallium arsenide also. So, with that I think we will conclude today. Tomorrow we will discuss this and go into the ohmic and rectifying contacts with metal. Okay.